Tonight, we turn our attention to the search for life beyond Earth, examining the methods scientists use to look for living organisms or signs of past life elsewhere in the universe. This is not speculation or science fiction. It is observational science. Astronomers detecting planets around distant stars. Spacecraft analyzing atmospheres and surfaces. Radio telescopes listening for signals. The search proceeds through measurement and evidence, guided by what we know about life on Earth and the conditions that support it. We will move through these ideas without excitement or urgency. The search for life beyond Earth is methodical work involving careful observation, statistical analysis, and patient instrument development. So far, we have not found confirmed evidence of life elsewhere, but the search itself teaches us about planets, stars, chemistry, and the conditions that make a world potentially habitable. We approach this subject with clarity and patience, distinguishing between what we observe, what we infer, and what remains unknown. Before we can discuss searching for life beyond Earth, we need to establish what scientists mean by certain fundamental terms. These concepts involve defining life itself, understanding what makes a world habitable, and clarifying what we search for. Life, in biological terms, is difficult to define precisely. Scientists generally describe life as a self-sustaining chemical system capable of evolution through natural selection. Living things take in energy from their environment, maintain internal organization against entropy, reproduce with inheritance, and change over generations through mutation and selection. These criteria work well for life on Earth, but may not capture all possible forms life could take elsewhere. For practical purposes, searches for life focus on life as we know it. Carbon-based organisms using water as a solvent. This is not because we assume all life must be like Earth's life, but because we understand this type of life thoroughly and know what signatures it produces. Carbon forms complex molecules readily. Water remains liquid over a wide temperature range and dissolves many substances. Together, they provide a versatile chemistry for life. We search for what we can recognize. Biosignatures are observable indicators of biological activity. On Earth, life produces distinctive chemical fingerprints. Oxygen in our atmosphere exists in large quantities because photosynthetic organisms produce it. Without life constantly replenishing it, oxygen would react with rocks and disappear. Methane combined with oxygen is another potential biosignature. Both gases react together, so their coexistence suggests ongoing production, possibly biological. Other biosignatures might include specific molecules that life produces or unusual isotopic ratios in atmospheric gases. Technosignatures are observable indicators of technology. If civilizations exist elsewhere and use technology, they might produce detectable signals. Radio or optical transmissions, atmospheric pollution, artificial structures. SETI, the search for extraterrestrial intelligence, looks for such signals, particularly in radio wavelengths, where interstellar communication might be practical. A technosignature would be unmistakable evidence of intelligent life, but none has been confirmed despite decades of searching. The habitable zone is the region around a star where a planet with sufficient atmospheric pressure could maintain liquid water on its surface. This zone's boundaries depend on the star's temperature and luminosity. Hotter stars have habitable zones farther out. Cooler stars have them closer in. The concept is based on stellar physics and planetary energy balance, not speculation. However, habitable means conditions permit liquid water. It does not mean life exists there. Many factors beyond distance from the star affect habitability. Exoplanets are planets orbiting stars other than our Sun. Until the 1990s, we had no confirmed examples, though their existence seemed likely. Now we know of thousands, detected through multiple independent methods. Exoplanets range from gas giants larger than Jupiter to rocky worlds smaller than Earth, orbiting close to their stars or far away, in systems utterly unlike our solar system. Planets are categorized by size, composition, and orbital characteristics. Hot Jupiters are gas giants orbiting very close to their stars, completing orbits in days. Super-Earths are rocky planets, more massive than Earth, but smaller than Neptune. Mini-Neptunes are smaller gas planets. Earth-like or terrestrial planets are rocky worlds with sizes similar to Earth. Some orbit in habitable zones. These are candidates for closer study. What we mean by habitable requires care. A habitable zone planet could have conditions permitting liquid water, but actual conditions depend on atmospheric composition, thickness and circulation, volcanic activity, magnetic fields, and countless other factors. A planet in the habitable zone might be a frozen rock with no atmosphere, or a steaming greenhouse like Venus. Habitable means potentially suitable. It is not confirmation of suitability. SETI is an observational program using radio and optical telescopes to search for signals produced by other technological civilizations. The program makes no assumptions about whether such civilizations exist. It simply conducts searches using available technology. If signals were detected, they would be confirmed through repeated observations and independent verification. So far, SETI has detected no confirmed signals. This absence of detection is itself information, constraining how common or detectable such civilizations might be. The distinction between searching and finding is fundamental. Science often involves negative results, searches that do not find what they seek. This is not failure, it is data. Each search ruled out certain possibilities or set limits on how common something might be. The search for life beyond Earth has not yet found confirmed examples, but it has discovered thousands of planets, revealed diverse planetary systems, mapped chemical abundances in space, and refined our understanding of how life could arise elsewhere. These definitions form the foundation for understanding the search. Life is identified by particular chemical and biological signatures. Habitable zones are calculable from stellar physics. Exoplanets are detected through measurable effects on their stars. SETI listens for signals that would be clearly artificial. Each approach rests on observation and measurement, not speculation. The search proceeds whether we find life or not, because the search itself advances our understanding. To understand how the search for life beyond Earth became modern science, we must trace its development from speculation to systematic observation using increasingly sophisticated instruments. For centuries, people wondered whether life exists elsewhere in the universe. The question was philosophical, not scientific, because no method existed to test it. With the invention of the telescope in the 17th century, detailed observation of other worlds became possible, starting with Mars and the Moon. Early observers saw features that seemed to suggest Earth-like conditions, seasonal changes on Mars, supposed canals, polar ice caps. These observations, often overinterpreted, suggested Mars might harbour life. In the 19th century, speculation about Martian life peaked. Percival Lowell, an American astronomer, mapped what he believed were artificial canals built by an advanced civilization to transport water from polar caps to arid equatorial regions. These canals turned out to be optical illusions, patterns the eye and brain imposed on random surface features. But the idea of life on Mars captured public imagination and motivated more careful observation. The modern search began with radio astronomy. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a paper suggesting that radio wavelengths would be practical for interstellar communication. Radio waves travel through space with little absorption, and certain frequencies, like the 21 centimetre line of neutral hydrogen, would be known to any technological civilization. The following year, astronomer Frank Drake conducted Project Ozma, the first systematic SETI search, observing 2 nearby stars for several weeks. He detected no signals, but the method was established. Drake also formulated what became known as the Drake equation, a framework for organizing questions about factors affecting how many detectable civilizations might exist in the galaxy. The equation is not a predictive tool. Most of its terms are unknown, but it structures thinking about star formation rates, planetary occurrence, the origin of life, and the longevity of civilizations. It is a pedagogical framework, not a theory. SETI searches continued sporadically for decades, using increasingly sensitive radio telescopes and covering more stars and frequencies. Some searches detected interesting signals. The WOW signal in 1977 was a strong, narrow-band signal lasting 72 seconds, but it was never detected again despite follow-up observations, leaving it unexplained but unconfirmed as artificial. SETI remains an observational program without confirmed detections. The search for exoplanets revolutionized the field. Before the 1990s, we had no confirmed planets around other Sun-like stars. Detecting them was extraordinarily difficult. Planets are tiny and faint compared to stars. Several methods were proposed, but not yet successful. In 1992, astronomers discovered the first confirmed exoplanets orbiting a pulsar, a dead star remnant. These planets were unexpected and formed in extreme conditions, not candidates for life. In 1995, Michel Mayor and Didier Queloz detected the first planet around a Sun-like star, 51 Pegasi b. This planet was a hot Jupiter, a gas giant orbiting extremely close to its star. The discovery, confirmed quickly by other teams, proved that planets exist around normal stars and that our detection methods worked. Mayor and Queloz received the Nobel Prize in Physics in 2019 for this discovery. Following this breakthrough, exoplanet discoveries accelerated. Ground-based telescopes found hundreds of planets through radial velocity measurements and transits. NASA's Kepler mission, launched in 2009, revolutionized the field by continuously monitoring over 150,000 stars for transits. Kepler discovered over 2,600 confirmed exoplanets and thousands more candidates before its mission ended. Kepler showed that planets are common. Essentially, every star has planets on average. Small, rocky planets are more common than large gas giants. Many stars have planets in their habitable zones. The diversity of planetary systems is astonishing. Systems packed with planets close to their stars, eccentric orbits unlike anything in our solar system, planets around binary stars. The universe contains countless worlds. Mars exploration progressed from orbiters to landers to rovers. Viking landers in the 1970s carried experiments designed to detect biological activity. Results were ambiguous and generally interpreted as negative, though some remain debated. Later missions focused on understanding Mars's geology and history. Orbital observations and rover investigations showed that Mars once had liquid water on its surface. River valleys, ancient lake beds, minerals that form in water. Mars was once more Earth-like, raising the question of whether life ever arose there. The Curiosity rover, operating since 2012, found complex organic molecules preserved in ancient rocks and detected methane in the atmosphere that varies seasonally. Organic molecules alone do not prove life. They form through non-biological processes, but they show Mars has the raw materials for life. The Perseverance rover, arriving in 2021, is collecting samples for eventual return to Earth, where they can be analysed with the laboratory instruments far more sophisticated than anything sent to Mars. Europa, Jupiter's moon, and Enceladus, Saturn's moon, emerged as surprising candidates for life. Spacecraft observations revealed both moons have subsurface oceans of liquid water beneath icy shells. Europa's ocean is inferred from magnetic field measurements and surface features suggesting ice floats on liquid. Enceladus confirmed its ocean more directly. Cassini spacecraft flew through water plumes ejected from cracks in the ice and detected organic molecules and evidence of hydrothermal activity. These oceans, warmed by tidal heating from their giant planets, could potentially harbour life in environments similar to Earth's deep ocean hydrothermal vents. This history shows a progression from speculation to observation. Early ideas about Martian canals were overinterpretation of poor data. Modern searches use precise measurements, spectra of exoplanet atmospheres, chemical analysis of Martian rocks, detection of subsurface oceans through gravitational studies. Each discovery raises new questions and guides future searches. We have not found life, but we have found places to look and methods to use. The search is active science, not philosophical speculation. Understanding what we search for requires understanding life's requirements. Not just what Earth's life needs, but what any chemical system recognizing as life would plausibly require. This knowledge comes from biology, chemistry, and studies of extreme environments on Earth. Life as we know it, is carbon-based. Carbon atoms form stable bonds with many other elements: hydrogen, oxygen, nitrogen, phosphorus, sulfur. Carbon can form chains, rings, and three-dimensional structures, creating enormous molecular diversity. Proteins, DNA, lipids, and carbohydrates are all carbon-based. This versatility makes carbon the foundation of Earth's biochemistry. Silicon, the next most similar element, forms fewer stable bonds and less complex molecules. While silicon-based life is conceivable in theory, carbon-based life is what we understand and can recognize. Water serves as life's solvent on Earth. A solvent is a liquid in which chemical reactions occur. Water has useful properties. It remains liquid over a wide temperature range, dissolves many substances, and remains stable in the presence of most chemicals. Life's chemistry happens in aqueous solution. Cells are mostly water. Biochemical reactions require water. Other solvents are possible. Ammonia remains liquid at lower temperatures, for instance. But water is abundant in the universe and well suited for carbon chemistry. Searchers for life focus on environments where liquid water could exist. Energy is essential for life. Living things extract energy from their environment to maintain organization, grow, and reproduce. On Earth, life uses various energy sources. Photosynthetic organisms capture sunlight. Animals eat other organisms. Microbes near hydrothermal vents use chemical energy from reactions between hot water and minerals. An environment supporting life needs available energy: light, chemical gradients, heat flow. Without energy sources, life cannot sustain itself. Chemical building blocks must be available. Life requires not just carbon and water, but also nitrogen, phosphorus, and various other elements. Nitrogen is essential for proteins and nucleic acids. Phosphorus is central to energy metabolism and genetic material. These elements must be present in accessible forms. Fortunately, the necessary elements are widespread in the universe, formed in stars and distributed through space by supernovae. Observations show complex organic molecules in molecular clouds, comets, and meteorites. The raw materials for life are common. Temperature and pressure constrain where life can exist. Chemical reactions require kinetic energy. Molecules must move and collide. Too cold and reactions stop. Too hot and complex molecules break apart. Liquid water exists between 0 and 100 degrees Celsius at Earth's surface pressure. However, pressure affects these limits. At high pressure, water remains liquid above 100 degrees. At low pressure, it freezes or boils at lower temperatures. Life's temperature range depends on pressure and the specific chemistry involved. Extremophiles, organisms thriving in extreme environments, expanded our understanding of life's limits. Thermophiles live in hot springs above 90 degrees Celsius. Psychrophiles survive in Antarctic ice, at negative 15 degrees Celsius. Acidophiles thrive in water with pH near zero, like battery acid. Alkalophiles live in pH 12 environments, like soda lakes. Barophiles withstand pressures hundreds of times Earth's surface pressure in deep ocean trenches. Halophiles survive in saturated salt solutions. Radio-resistant organisms withstand radiation doses lethal to most life. These extremophiles show life is more adaptable than once thought. Early definitions of habitable zones were narrow, assuming life requires Earth-like temperature and pressure. Extremophiles broaden the possibilities. Environments previously considered sterile might support microbial life. This changes our search strategies. We look beyond Earth-like conditions to more diverse environments, including subsurface oceans, icy moons, and deep Martian underground. Atmospheres affect habitability in complex ways. An atmosphere regulates surface temperature through the greenhouse effect. Gases like carbon dioxide, methane, and water vapor trap heat. Without an atmosphere, a planet's surface temperature follows from simple energy balance with its star. With an atmosphere, the planet retains more heat. Thick atmospheres can keep a planet warm enough for liquid water even at greater distances from the star. Thin atmospheres provide little warming, and the planet may freeze despite being in the nominal habitable zone. Atmospheres also protect surfaces from harmful radiation. Earth's ozone layer shields the surface from ultraviolet light. Planets without protective atmospheres receive harsh radiation that could damage biological molecules. However, life could exist underground or underwater, protected from surface radiation. Mars's thin atmosphere provides little protection, but subsurface environments might harbour life. Time is an important consideration. Life on Earth emerged relatively quickly after conditions became suitable. Oceans formed about 4 billion years ago, and evidence for life appears by 3.8 billion years ago, perhaps earlier. This suggests that given suitable conditions, life may arise readily. However, the progression from simple microbes to complex multicellular organisms took billions of years. Photosynthesis emerged early, but animals appeared only in the last 600 million years. Searching for intelligent life means finding not just habitable planets, but those where life has had billions of years to evolve complexity. Planetary characteristics matter beyond temperature and atmosphere. Magnetic fields deflect charged particles from stellar winds, which could strip away atmospheres over time. Mars lost much of its atmosphere, partly because it lacks a global magnetic field. Earth's magnetic field, generated by its liquid iron core, protects our atmosphere. Plate tectonics recycles materials, regulates atmospheric carbon dioxide, and may be important for long-term habitability. Whether plate tectonics is necessary for life is debated, but it affects planetary evolution. These requirements, liquid water, carbon chemistry, energy sources, appropriate temperatures and pressures, protective environments, and sufficient time guide the search for life. They are not arbitrary assumptions, but are based on our understanding of chemistry, physics, and biology. We search for environments meeting these criteria because we know life can exist there. Whether life requires all these factors or could exist under radically different conditions remains unknown. We search for what we understand, knowing we might miss exotic forms of life that differ fundamentally from Earth's. Core concepts, detection methods. Finding life beyond Earth requires detecting it across vast distances or on other worlds we can visit with robotic spacecraft. The methods scientists use depend on the type of life we search for and the tools available. Each method has strengths and limitations, and multiple approaches improve the chances of success. The transit method detects exoplanets by measuring the slight dimming of a star when a planet passes in front of it from our viewpoint. Imagine watching a distant streetlight. If something crosses between you and the light dims briefly. Planets do this to their stars. The dimming is tiny, about 1% for a Jupiter-sized planet, and only 0.01% for an Earth-sized planet transiting a Sun-like star. But sensitive instruments can measure such changes. The transit method reveals more than just the planet's existence. The amount of dimming tells us the planet's size. The time between transits tells us the orbital period. From the period and stellar properties, we calculate orbital distance and determine if the planet lies in the habitable zone. Multiple transits allow precise measurements. The Kepler mission used this method to find thousands of planets. The radial velocity method detects planets through their gravitational effect on the star. A planet's gravity pulls on its star, causing the star to wobble slightly. We cannot see this wobble directly across vast distances, but we can measure it spectroscopically. As the star moves toward us, its light is slightly blue shifted to shorter wavelengths. As it moves away, its light is red shifted. These Doppler shifts are tiny but measurable with high precision spectrographs. Radial velocity measurements reveal the planet's mass, or rather a minimum mass if the orbit is not edge-on. Combined with transit observations, which give size, we can estimate density and determine if a planet is rocky, gaseous, or icy. The first exoplanets around Sun-like stars were discovered using radial velocity. The method works well for large planets close to their stars, but struggles with small, distant planets because the stellar wobble is smaller. Direct imaging captures pictures of planets by blocking the star's light. This is extraordinarily challenging. A star is millions or billions of times brighter than its planets. Advanced techniques use coronagraphs or star shades to block starlight, allowing faint planets to be photographed. Direct imaging works best for large planets orbiting far from young stars, where planets are still hot from formation and emit infrared light. Only a few dozen planets have been directly imaged, but the method provides unique information. We can take spectra of the planet's light, potentially detecting atmospheric gases. Gravitational microlensing exploits Einstein's general relativity. When a foreground star passes in front of a background star, from our perspective, the foreground star's gravity bends and magnifies the background star's light. If the foreground star has a planet, the planet's gravity creates an additional brief brightening. Microlensing events are rare and unpredictable. Each occurs once and cannot be repeated. But the method can detect planets at large distances from Earth and planets far from their stars, complementing other methods. Atmospheric spectroscopy analyzes the composition of exoplanet atmospheres by observing how starlight filters through the atmosphere during transits. Different gases absorb light at specific wavelengths, creating absorption features in the spectrum. By comparing the star's spectrum during transit with the spectrum outside transit, we isolate the planet's atmospheric absorption and identify gases present. This technique has detected water vapor, carbon dioxide, methane, and other molecules in several hot Jupiter atmospheres. For smaller rocky planets, detecting atmospheric gases is much harder. The signal is weaker, and observing time required is longer. The James Webb Space Telescope, launched in 2021, has the sensitivity to study Earth-sized planet atmospheres in detail. This is where we might find biosignatures, combinations of gases suggesting biological activity. Biosignatures in atmospheres could include oxygen combined with methane or phosphine in certain contexts, or unusual abundances of gases requiring ongoing production. Oxygen is especially interesting because it is highly reactive and should disappear from atmospheres unless replenished. On Earth, photosynthetic life produces oxygen. Detecting oxygen on an exoplanet would not prove life. Oxygen can be produced by non-biological processes like water vapor being split by ultraviolet light, but it would warrant closer study. Radio telescope searches for techno-signatures involve monitoring stars and regions of space for artificial radio signals. Natural radio sources exist, pulsars, masers, plasma processes, but they have characteristic features: broad bandwidth, regular pulses, or specific mechanisms. An artificial signal might be narrowband, at unusual frequencies, or modulated in ways suggesting information content. SETI searches examine millions of frequency channels simultaneously, looking for signals that stand out. The Breakthrough Listen project, funded privately, conducts the most comprehensive SETI search to date. It uses major radio telescopes, Parkes in Australia, Green Bank in the United States, to observe millions of nearby stars across billions of frequency channels. It also searches for optical laser pulses, which could be used for interstellar signaling. After years of observations, no confirmed techno-signatures have been detected. This constrains how common detectable technological civilizations are, or how they might communicate. The Drake equation organizes thinking about factors affecting detectable civilizations. It multiplies together the star formation rate, the fraction of stars with planets, the number of habitable planets per planetary system, the fraction on which life arises, the fraction where intelligence evolves, the fraction that develop detectable technology, and the length of time such civilizations remain detectable. The result estimates the number of detectable civilizations in the galaxy at any given time. Most terms in the Drake equation are poorly known. We now understand star formation rates and planet occurrence fairly well. The fraction of planets where life arises is unknown. The progression to intelligence, technology, and longevity are highly speculative. The equation is not predictive, but helps structure questions. It shows what we need to understand to answer whether we are alone. Statistical approaches examine large samples. Kepler's data allowed statistical analysis of planet occurrence rates. We now know small planets are common, and roughly 20 to 50% of Sun-like stars have planets in the habitable zone. These statistics guide target selection for follow-up studies. We focus on systems where habitable planets are most likely. These methods, transit observations, radial velocity, direct imaging, spectroscopy, radio searches, statistical analysis, together form a comprehensive search strategy. Each method contributes different information. Transit photometry finds planets and determines sizes. Radial velocity measurements determine masses. Spectroscopy probes atmospheres. Radio searches look for technology. No single method provides complete answers, but combined, they enable systematic exploration of whether life exists beyond Earth. The search for life beyond Earth is not abstract theory. It proceeds through specific observations of particular worlds and systems. Examining concrete examples illustrates what we have found and what observations reveal. Proxima Centauri b is the nearest known exoplanet in a habitable zone, orbiting the closest star to our Sun, about 4.2 light-years away. Discovered in 2016 through radial velocity measurements, Proxima Centauri b has a minimum mass about 1.3 times Earth's mass, suggesting it could be rocky. It orbits every 11 days, which seems fast but is appropriate for Proxima Centauri, a small red dwarf star much cooler than the Sun. The planet orbits within the habitable zone, where liquid water could exist. However, red dwarfs present challenges for life. They emit intense flares, sudden eruptions of radiation and charged particles that could strip away atmospheres or sterilize surfaces. Proxima Centauri is particularly active, flaring frequently. Whether Proxima Centauri b retains an atmosphere and whether conditions are truly habitable remain unknown. Proximity makes this planet a priority target for future observations, but proximity does not guarantee habitability. The TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets orbiting an ultra-cool dwarf star. Discovered through transits beginning in 2016, with all 7 planets confirmed in 2017, this system is remarkable because multiple planets orbit in the habitable zone. The planets are designated TRAPPIST-1b through H, with letters indicating orbital order. Planets E, F, and G orbit where liquid water could exist. Transit observations revealed the planets' sizes, all similar to Earth. Radial velocity measurements constrained their masses, showing they are rocky. Some planets may have substantial water content. They might be water worlds with deep oceans covering their surfaces. Detailed atmospheric studies are planned with the James Webb Space Telescope, which can determine if these planets have atmospheres and what gases they contain. This system provides multiple targets for searching for biosignatures. However, TRAPPIST-1 is also a red dwarf, raising questions about flares and atmospheric erosion. The planets orbit very close to their star, closer than Mercury to the Sun, but the star is so cool that these orbits place planets in the habitable zone. Tidal forces might lock the planets, so one side always faces the star, creating extreme day-night temperature differences. Whether such planets can maintain stable climates is debated. Observations will reveal whether atmospheres exist and what they contain. Mars remains a primary target for astrobiology within our solar system. Decades of orbital and surface observations show Mars once had liquid water. Ancient river valleys, deltas, lake beds, and minerals that form only in water are preserved in the geology. About 3 to 4 billion years ago, Mars was warmer and wetter, with conditions potentially suitable for life. What happened to Mars's water? Some escaped to space, and much is now frozen in polar caps and underground ice. The Curiosity rover has analysed rocks in Gale Crater, an ancient lake bed. Measurements showed the lake waters were neutral pH, contained essential elements for life, and provided chemical energy sources. Organic molecules, complex carbon-based compounds, are preserved in ancient sediments. These organics could be from ancient Martian life, or from meteorites, or from non-biological chemistry. We cannot tell from current data. The presence of organics shows Mars has the chemical building blocks for life. Methane detections in Mars's atmosphere add intrigue. Methane is destroyed by sunlight over a few hundred years, so its presence indicates ongoing production. Sources could be geological, reactions between water and minerals in the crust, or biological. On Earth, most methane is biological. Measurements show methane varies seasonally and spatially, suggesting localized sources. Neither explanation is confirmed. Understanding methane requires more observations and eventually sample return. Perseverance rover, operating in Jezero Crater since 2021, collects rock samples for eventual return to Earth. Jezero was an ancient lake filled by a river, preserved in delta deposits. If Mars ever had life, such environments are good places to look. Samples will be cached on Mars's surface, retrieved by a future mission, and returned to Earth for analysis with laboratory instruments far more sophisticated than what can be sent to Mars. Sample return could provide definitive answers about Martian life. Europa, Jupiter's moon, is covered by an ice shell floating on a subsurface ocean. The ocean is inferred from several lines of evidence. Europa's magnetic field interacts with Jupiter's in ways indicating a conductive liquid beneath the ice. The surface shows features suggesting ice fractures and reshapes as it floats, and Europa's shape is consistent with an internal ocean. The ocean is kept liquid by tidal heating. Europa's eccentric orbit around Jupiter flexes the moon, generating internal heat through friction. Europa's ocean may be in contact with the rocky sea floor, allowing chemical reactions between water and minerals that could provide energy for life, similar to hydrothermal vents on Earth's ocean floor. The ocean is salty, inferred from spectroscopic observations of the surface. Plumes of water vapour have been detected erupting from the surface, though observations are difficult. These plumes offer the tantalising possibility of sampling ocean material without drilling through kilometres of ice. NASA's Europa Clipper mission, launching in the 2020s, will perform dozens of close flybys of Europa, mapping the ice shell thickness, confirming the ocean's extent, and searching for plumes. If plumes are active, the spacecraft could fly through them and analyse their composition, potentially detecting organic molecules or other indicators of habitability. This mission will determine whether Europa's ocean is a promising target for a future mission that could land and drill through the ice. Enceladus, Saturn's small moon, confirmed its subsurface ocean more directly. The Cassini spacecraft repeatedly flew through water plumes erupting from cracks near the South Pole. Analysis of plume material showed water ice grains, salts, silica particles indicating hot water rock interactions, and complex organic molecules, including some with masses suggesting biological interest. The plumes originate from an ocean beneath an ice shell, warmed by tidal heating from Saturn. The plumes make Enceladus accessible. We do not need to land and drill. A mission could fly through plumes repeatedly, collecting samples and analysing them. The presence of hydrothermal activity inferred from the silica particles suggests energy sources available for life. Enceladus demonstrates that small icy moons can have active, potentially habitable oceans. Titan, Saturn's largest moon, has a thick nitrogen atmosphere, liquid hydrocarbon lakes on its surface, and an organic, rich environment. Titan is too cold for liquid water. Temperatures are around -180 degrees Celsius, but methane and ethane are liquid there. Complex organic chemistry occurs in the atmosphere, driven by sunlight breaking apart methane and nitrogen, creating complex molecules that rain onto the surface. Titan may also have a subsurface water ocean beneath an icy crust. Could life exist in Titan's hydrocarbon lakes? Water-based life cannot, but hypothetical life using different chemistry might. This is speculative, but Titan's organic richness makes it interesting for astrobiology. The Dragonfly mission, a nuclear-powered helicopter, will explore Titan in the 2030s, analysing surface composition and searching for chemical signs of past or present life. These examples, Proxima Centauri b, TRAPPIST-1 planets, Mars, Europa, Enceladus, Titan, show the diversity of targets in the search for life. Each world presents different conditions and challenges. Some are nearby and accessible to robotic exploration. Others are distant but observable from Earth. Each observation constrains where and how life might exist beyond Earth and guides future missions. The search for life beyond Earth connects to many scientific disciplines, drawing on planetary science, chemistry, biology, and even philosophy. Understanding these connections clarifies what we search for and how discoveries would reshape knowledge. Astrobiology is the interdisciplinary field studying the origin, evolution, distribution, and future of life in the universe. It combines astronomy, biology, chemistry, geology, and planetary science. Astrobiologists study extremophiles to understand life's limits, analyze meteorites for organic compounds, model planet formation, and design instruments for detecting biosignatures. Astrobiology is not speculative. It is grounded in observations and experiments, though it addresses possibilities as well as certainties. Planetary science provides context for understanding habitable environments. Planetary formation theory explains how planets arise from protoplanetary disks of gas and dust around young stars. The composition, size, and orbit of planets depend on where they form and how the disk evolves. Rocky planets form in the warm inner regions where metals and silicates condense. Gas giants form in colder outer regions where ices are abundant. Understanding formation helps predict which systems might have habitable planets. Spectroscopy, the analysis of light's interaction with matter, is central to remote sensing. Every molecule absorbs and emits light at characteristic wavelengths. By analyzing the spectrum of light from or through an atmosphere, we identify molecules present. Spectroscopy revealed the composition of stars, showing they are made of hydrogen and helium. It revealed organic molecules in space. It will reveal exoplanet atmospheric compositions and potentially detect biosignatures. The question of why we haven't detected signals from other civilizations is sometimes called the Fermi observation, associated with physicist Enrico Fermi. Fermi supposedly asked, "Where is everybody?" noting that if technological civilizations are common and galaxy-crossing travel or communication is feasible, we should see evidence, spacecraft, probes, signals. We do not, or at least we have not, confirmed any despite searching. This observation is empirical. We have looked and found silence. Multiple explanations exist, all speculative. Perhaps life is rare, perhaps intelligence is rare, perhaps technological civilizations destroy themselves or lose interest in communication. Perhaps interstellar travel is impractical. Perhaps civilizations exist but use communication methods we do not recognize. Perhaps we have not searched long enough or thoroughly enough. Perhaps we are alone in the galaxy or even the observable universe. Each explanation is consistent with current observations, and we lack data to distinguish among them. This is not a paradox in the logical sense. It is an observation that requires explanation. The absence of detected signals informs search strategies. It suggests that if civilizations exist, they are either rare, distant, brief-lived, or communicate in ways we do not detect. Or perhaps civilizations are common but avoid revealing themselves. We cannot know without more observations. The situation illustrates how science proceeds with incomplete information. We observe, formulate hypotheses, and continue searching. Future missions will enhance our capabilities. The James Webb Space Telescope observes in infrared wavelengths, allowing it to study exoplanet atmospheres in detail. It has already observed exoplanet atmospheres, detecting water, carbon dioxide, and other molecules. For smaller rocky planets in habitable zones, extended observation campaigns will search for biosignatures. These observations are planned and will occur over the next decade. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, will survey the galaxy for exoplanets using microlensing and direct imaging. It will discover thousands of planets, including many in habitable zones. Europa Clipper will explore Europa's ocean habitability. Dragonfly will explore Titan's surface. Mars Sample Return will bring Martian rocks to Earth for detailed analysis. Each mission contributes pieces to the larger picture. Technological limitations constrain what we can observe. Detecting Earth-like planets around Sun-like stars is challenging. The planet is small, the transit signal is weak, and the star is brighter. Detecting biosignatures in exoplanet atmospheres requires long observation times with the most sensitive instruments. Reaching Mars takes months. Reaching the outer solar system takes years or decades. Interstellar distances are vast. Even the nearest stars are years away at light speed. But technology advances. Telescopes become more sensitive. Spectrographs achieve higher resolution. Mission designs improve. Computational methods extract more information from data. Each advance enables observations previously impossible. The search for life beyond Earth has progressed enormously in the past few decades and will continue advancing. What finding life would mean depends on what we find. Discovering microbial life on Mars or Europa would answer the question of whether life arose independently elsewhere. It would show life is not unique to Earth, increasing the likelihood it exists throughout the universe. Discovering intelligent life or technology would be even more profound. It would show we are not alone as intelligent beings. It would raise questions about communication, contact, and humanity's place in the cosmos. What not finding life would mean is harder to interpret. Absence of evidence is not evidence of absence, as the saying goes. We have searched a tiny fraction of the galaxy, a few thousand stars out of hundreds of billions. We have explored a handful of solar system bodies in detail. Negative results constrain possibilities but do not rule them out. Life could be common but beyond our current detection capabilities. Or it could be rare, and we are among the first civilizations in the galaxy. Or we could be truly alone. We cannot know from current data. Science proceeds through observation, whether we find what we seek or not. The search for life beyond Earth has revealed thousands of planets, expanded our understanding of planetary habitability, and driven technological development. These advances have value regardless of whether we find life. The search continues because the question is fundamental and because the search itself produces knowledge. As we move toward the close of our discussion, we can restate gently some of the central ideas we have explored. The search for life beyond Earth proceeds through careful observation and measurement. Scientists use multiple methods to detect exoplanets: the transit method, radial velocity, direct imaging, and microlensing. These methods have found over 5,000 confirmed planets, showing that planets are common throughout the galaxy. Some orbit in habitable zones where liquid water could exist on their surfaces. Life, as we know it, requires liquid water, carbon-based chemistry, energy sources, and appropriate conditions of temperature and pressure. These requirements guide where we search. Mars once had liquid water and conditions potentially suitable for life. Europa and Enceladus have subsurface oceans that could harbour life in environments similar to Earth's deep ocean vents. Some exoplanets orbit in habitable zones of their stars and are targets for atmospheric studies. Biosignatures are observable indicators of biological activity. Certain combinations of atmospheric gases, oxygen with methane, for instance, would suggest ongoing biological processes. Technosignatures are indicators of technology, such as artificial radio signals. SETI searches for such signals using radio telescopes. So far, no confirmed biosignatures or technosignatures have been detected. This absence is itself observational data. The transit method and radial velocity measurements reveal planet sizes, masses, and orbits. Atmospheric spectroscopy analyzes light filtering through exoplanet atmospheres during transits, identifying gases present. The James Webb Space Telescope is capable of detecting atmospheric gases in Earth-sized planets' atmospheres, potentially including biosignatures. Observations are ongoing and will continue for years. Mars exploration has revealed evidence for ancient liquid water, organic molecules, and methane in the atmosphere. Whether life ever arose on Mars remains unknown. The Perseverance rover is collecting samples for eventual return to Earth, where detailed laboratory analysis could provide definitive answers. Europa and Enceladus have subsurface oceans in contact with rocky seafloors, providing possible energy sources for life. Europa Clipper will explore Europa's ocean in detail. Plumes from Enceladus offer the possibility of sampling ocean material directly. These moons are priority targets for astrobiology. SETI has searched for decades without confirmed detections of artificial signals. This constrains how common or detectable technological civilizations might be, but does not rule them out. The breakthrough. Listen Project conducts the most comprehensive search to date, observing millions of stars across billions of radio frequency channels. The observation that we have not detected signals from other civilizations, sometimes framed as a question rather than a paradox, reflects our current observational reality. Multiple explanations exist, all speculative. The observation informs search strategies, but does not provide definitive answers about whether life or intelligence exists elsewhere. The Drake equation organizes questions about factors affecting the number of detectable civilizations. Most factors are unknown. The equation is a framework for thinking, not a predictive tool. Recent progress in understanding planet occurrence helps constrain some factors, but others remain deeply uncertain. Extremophiles on Earth demonstrate that life can survive in conditions once thought impossible. Extreme temperatures, pressures, acidity, salinity, and radiation. This expands the range of environments we consider potentially habitable and guides searches to more diverse locations. The search for life beyond Earth is active science, proceeding through observations that are published, reviewed, and tested. Discoveries are announced when confirmed through independent verification. Negative results, searches that do not find what they seek, are also informative. Science advances whether we find life or not because observations constrain possibilities and guide future research. We have moved through these ideas slowly, examining methods, targets, and observations without speculation. The search is grounded in physics, chemistry, and biology. It proceeds methodically using the best available instruments and techniques. Whether we find life beyond Earth remains unknown, but the search continues, advancing our understanding of planets, stars, chemistry, and the conditions that make worlds habitable. We have now travelled through the methods and targets in humanity's search for life beyond Earth, the exoplanet detection techniques that revealed thousands of worlds, the observations of Mars, Europa, and Enceladus showing potentially habitable environments, the SETI searches listening for signals, and the framework of requirements that guide where we look. We have seen that this search is careful science, proceeding through observation and measurement. There is no need to retain every detail. The search for life involves many specialized methods and diverse targets, each with particular challenges and possibilities. Understanding develops through patient attention to what observations reveal. You may have drifted in and out as we spoke, and that is entirely natural. Each section we discussed was intended to stand on its own, so that wherever your attention rested, you encountered ideas that were complete in themselves. The question of whether life exists beyond Earth is profound. The search for answers proceeds not through speculation, but through systematic observation. Telescopes studying distant planets, rovers analysing Martian rocks, spacecraft exploring icy moons. We have not yet found confirmed evidence of life elsewhere, but the search has transformed our understanding of the universe. We know planets are common. We know the ingredients for life are widespread. We know environments that could support life exist in our solar system and likely around other stars. We close gently, without urgency, as we began. The search continues. New observations are made. Instruments improve. Missions launch. Questions that seem unanswerable today may be answered in years or decades through patient work. Or they may remain open, reminding us that much about the universe remains to be discovered. The search itself is valuable, expanding knowledge, whether we find what we seek or not. Rest now, if you wish. There is nothing more required of you tonight.